Hello, in this lecture we'll find out the radius of a circle using two different methods. In the drawing we have triangle ABC that blocks the circle, or the circle is inscribed by triangle ABC. In addition, we know that this angle ABC equals to 60 degrees. This is angle ACB that is equal to 70 degrees in its size. And side BC equals to 2 units in its length. Again, our mission is to find out the radius R of this circle. So we start with the first method, and we'll do a construction, that is to say, from point C we'll draw perpendicular on side AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. In the next step, I will copy the right triangle BDC in a new page, and we will analyze this right triangle BDC. So actually, this is the right triangle BDC that I copied from the original drawing. Angle DBC equals to 60 degrees, and side BC equals to 2 units according to what is given as the question. In this right triangle BDC, cosine 60 degrees equals to BD over BC. Cosine 60 degrees equals to BD over BC. So it is BD over BC. BC is 2, so it is BD over 2. Cosine 60 degrees is 1/2. So in total, we found out that 1/2 equals to BD over 2. Here we multiply this equation by 2. And finally we get that BD equals to 1 unit in its length. So this is side BD that equals to 1 unit in its length. We continue to focus on the right triangle BDC. This right triangle BDC, sinus 60 degrees equals to DC over BC. Okay, so sinus 60 degrees is equal to 3 over 2. That equals to DC over BC. BC is 2. So in total, we found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2. And finally we get that DC equals to the square root of 3 units in its length. So here DC equals to the square root of 3 units in its length. So in the right angle BDC, the sum of the angles must be equal to 180 degrees. According to the rule, that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside the angle DBC? We have this angle that is 90 degrees, plus this angle that is 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. Therefore, this missing angle must be equal to 30 degrees. So I write it down. So it is given us the question that the big angle ACB equals to 75 degrees. This is the big angle that is equals to 75 degrees. The small angle BCD equals to 30 degrees. Therefore, the missing angle here must be equal to, this is the missing angle, that it must be equal to the big angle minus the small angle. The big angle is 75 degrees minus the small angle that is 30 degrees. It is equals to 45 degrees. So we can find out that the missing angle ACD equals to 45 degrees in its size. So I will copy the right triangle ACD in a new page, and we will analyze this right triangle ACD. So actually, this is the right triangle ACD that I copied from the original drawing. We just right now found out that the angle ACD equals to 45 degrees in its size, and side DC equals to the square root of 3 units in its length. In this right triangle ACD, the sum of the angles must be equal to 180 degrees. So which angles we have inside this right triangle ACD? We have this angle that is 90 degrees, plus this angle that is 45 degrees. 90 degrees plus 45 degrees, it is 135 degrees. Therefore, the missing angle here must be equal to 45 degrees in its size. In order to complete the sum of the angles in this right triangle ACD to 180 degrees, the missing angle here must be equal to 45 degrees. So those two angles are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. That is to say, in front of those two equal angles, we have those two sides that must be equal to each other. That is to say, side AD must be equal to side DC. AD equals to DC. But we have only found out that DC equals to the square root of units in its length. So we can write here that DC equals to the square root of units. And from this equation, AD equals to CD equals to the square root of units. We will derive that AD is also equals to the square root of units in its length. AD equals to the square root of units in its length. Can write here that line segment AD equals to the square root of units in its length. We continue to focus on this right triangle ADC. In the right triangle ADC, according to the Pythagoras theorem, here by PT is the progression for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse here is AC. The square of the hypotenuse is AC square, and it must be equal to AD square plus DC square. So AC square equals to AD square. AD is equal to 3, therefore AD square is equal to 3 square, that is 3, plus DC square. DC is also equal to 3, therefore DC square is equal to 3 square, that is 3. In total, AC square equals to 3 plus 3, that is 6, so AC square equals to 6. Here we take a root out of this equation, and finally we get that AC equals to the square root of 6 units in its length. AC equals to the square root of 6 units in its length. Here, side AC of triangle ABC equals to the square root of 6 units in its length. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is described by triangle ABC is equal to, the radius R equals to the area of triangle ABC over S. S is the semi-perimeter of the same triangle, triangle ABC, and the semi-perimeter of any triangle is equal to the perimeter over 2. So the drawing of rule number 15 is here. This is the drawing. So we have in the drawing a circle that is inscribed by this triangle, triangle ABC, or triangle ABC blocks this circle. So the radius R of this circle equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. So we can actually implement rule number 15 in our drawing. Whenever we have a circle that is inscribed by a triangle, we can implement rule number 15. Therefore, we can implement rule number 15 in our drawing. So, according to rule number 15, the radius R of this circle that is inscribed by triangle ABC will be equal to the area of triangle ABC over the semi-perimeter of the same triangle, triangle ABC. Repeat again. According to rule number 15, the radius R of our circle, that is the radius that we are looking for in this question, the radius R, according to rule number 15, equals to the area of triangle ABC over the semi-perimeter of the same triangle, triangle ABC. The area of any triangle equals to the base of the triangle times the height to the base over 2. So, and we have to divide it by S, that is the semi-perimeter of the same triangle, triangle ABC. Okay. So, we'll choose the base of this triangle, triangle ABC is AB. The base is AB. And therefore, the height to the base is CD. Why? Because CD creates 90 degrees with the base AB. So the height is CD divided by 2. This expression is the area of triangle ABC, and we have to divide the area of triangle ABC by S. S is the semi-perimeter of triangle ABC. The semi-perimeter of any triangle is the perimeter over 2. The perimeter is the sum of its side lengths. The sum of its side lengths is AB plus AC plus BC. So S equals to the perimeter that is AB plus AC plus BC. If we divide the perimeter by 2, we get the semi-perimeter S. So in total, the semi-perimeter of triangle ABC equals to AB plus AC plus BC over 2. So here, AB equals to the square root of 3 plus 1. Times CD. CD equals to the square root of 3 divided by AB. AB again is square root of 3 plus 1 plus AC. We already found out that AC equals to the square root of 6 plus BC. BC equals to 2 units according to what is given as the question. And we have to divide the perimeter by 2. So actually, this expression is the area of triangle ABC, and the value of this expression is 2.366. That is to say, the area of triangle ABC equals to 2.366 square units divided by this expression that is actually the semi-perimeter of the same triangle ABC. The value of this expression in total it is equals to 3.591 units. And 2.366 over 3.591 equals to 0.6589 units. In conclusion, we found out that the radius R of this circle, that is the radius that we are looking for, equals to 0.6589 units. And that is the answer to the question. In the next step, I will present to you how to find out the radius of this circle according to the second method. In the second method, we define the center of this circle, this point, as O. We define the point of tendency of tangent AC with this circle as F. We define the point of tendency of tangent AB with this circle as E. And finally, we define the point of tendency of tangent BC with this circle as D. Here, point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle, and we actually define the radius of this circle as R. And here we have rule number 1 that we can implement in our drawing. According to rule number 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So we have in the drawing tangent AB, that is tangent to this circle point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. You can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, then this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we join points O and D together by straight line. OE is the radius of this circle that is equal to R. Again, you can implement rule number 1 because the radius OE is drawn to point E, that is the point of tendency of tangent AB with this circle. And whenever your radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. If AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we join points O and F together by straight line. Again, OF is the radius of this circle that is equal to R, and we have the radius OF that is drawn to point F, that is the point of tendency of tangent AC if this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius FO. If AC is perpendicular to FO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule number 1. We can implement here also rule number 2. I'll remind you quickly what is rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing we have a circle and we have the common standpoint point P. From the common standpoint point P we have two tangents to this circle, tangent PA and tangent PB. And according to this one, rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing. Why? Because in our drawing, we have, if we focus on the common external point, if we focus on the common external point C, from the common external point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD. CF equals to CD according to rule number 2. Likewise, we will focus on the common standpoint point B. For the common standpoint point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD. BE equals to BD according to the same rule, rule number 2. In the next step, we join points O and C together by a straight line. And we join points O and B together by a straight line. In the next step, we prove that those two right angles can go into each other. That is to say, we prove that the green right angle BOD is congruent to the yellow right triangle BEO. So writing down, we prove that the green right triangle BOD is congruent to the right yellow triangle BOE. So what those two right triangles can go into each other? First of all, side EO of the yellow triangle equals to side OD of the green triangle. They are both the radii of the circle, therefore they are equal to each other. They are equal to R. So, so I write it down. Repeat again. EO equals to OD because they are both the radii of the circle, therefore they are equal to each other. In addition, side EB of the yellow triangle equals to side BD of the green triangle according to rule number 2. Here, BE equals to BD according to rule number 2. So I write it down. Repeat again. BE equals to BD according to rule number 2. And finally, OB is the current side that belongs to both triangles, so we can write down that OB equals to itself is the current side that belongs to both triangles. Repeat again. OB equals to itself is the current side that belongs to both triangles. So actually prove that all the three sides of the green triangle BOD are correspondingly equal to all the three sides of the yellow triangle EOB. Therefore, those two right triangles can go into each other according to side rule. So I write it down. The green triangle BOD congruent. This is the sign of congruent to the yellow triangle BOE according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other. So this is angle EBO in the yellow triangle, and it equals to angle OBD in the green triangle. So again, angle EBO equals to angle OBD. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other. Therefore, the two corresponding angles, must be also equal to each other. So if we define this angle as theta, then the other angle must be also equal to theta because they are equal to each other. So if this angle equals to theta, then the other angle must be also equal to theta. And therefore, here we have theta plus theta that is 2 theta equals to 60 degrees. 2 theta equals to 60 degrees. We divide this equation by 2 and finally we get that angle theta equals to 30 degrees in its size. So actually this is angle theta is equal to 30 degrees in its size. In the next step, I'm copy the right green triangle BOD. In your present, we analyze this right green triangle BOD. So actually, this is the green right triangle BOD that I copied from the original drawing. This is angle theta that is equal to 30 degrees in size, and side OD is the radius of the circle that is equal to R according to our definition. So in this right triangle BOD, tangents 30 degrees equals to OD over BD. So tangent 30 degrees equals to OD. OD is R, so it is, we substitute OD by R. So it is R over BD. Tangent 30 degrees equals to R over BD. Here we multiply this equation by BD and we get that BD times tangents 30 degrees equals to R. Here we divide this equation by tangents 30 degrees and finally we get that BD equals to R over tangents 30 degrees. So this line segment BD equals to R over tangents 30 degrees in its length. So I write it down. We repeat on the same process on those two right angles. So we do it quickly because we have already done it on those two right angles. We prove that the right orange triangle ODC is congruent to the right pink triangle OFC. So I write it down. We prove that the orange right triangle ODC is congruent To the right, pink triangle, triangle OFC. So what those two right triangles can point to each other? First of all, OF equals to OD. They are both the radii of the circle, therefore they are equal to each other. OF, side OF of the pink triangle equals to side OD of the orange triangle. They are both equal to R because they are both radii of the circle, therefore they are equal to each other. In addition, CF equals to CD according to rule number 2. CF equals to CD, CF equals to CD according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself, it's a common side. So actually proved that all the three sides of the pink triangle OFC are correspondingly equal to all the three sides of the orange triangle ODC. Therefore, those two right triangles can point to each other according to side rule. So I write it down. The pink triangle OFC is congruent to the orange triangle ODC according to side rule. And for the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. Okay. So angle FCO in the pink triangle equals to angle OCD in the orange triangle. If we define one of the angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. So 2 alpha equals to 75 degrees. Repeat again. 2 alpha equals to 75 degrees. We divide this equation by 2 and get that alpha equals to 37.5 degrees. So actually this is angle alpha is equals to 37.5 degrees. In the next step I will copy the orange triangle ODC in a new page and we'll analyze this orange triangle ODC. So actually this is the orange triangle ODC that I copied from the origin drawing. This is angle alpha that is equals to 37.5 degrees and side OD is the radius of the circle that is equal to R according to our definition. So in this right triangle ODC, tangents 37.5 degrees equals to OD over DC. OD is R, So we substitute OD by R, and we get that tangent 37.5 degrees equals to R over DC. Again, tangent 37.5 degrees equals to R over DC. Here we multiply this equation by DC, and we get that DC times tangent 37.5 degrees equals to R. Here we divide this equation by tangent 37.5 degrees, and finally we get that DC equals to R over tangent 37.5 degrees. So actually, this 9 segment DC equals to R over times 37.5 degrees. So I write it down here in the original in this drawing. DC equals to R over tangent 37.5 degrees. From the drawing, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. So I write it down. BC equals to BD plus DC. Repeat again. Side BC equals to BD plus DC. It is given us the question that BC equals to 2 units in itself, so we substitute BC by 2, and it is equals to BD plus DC. BD is R over tangent 30 degrees, so we substitute BD by R over tangent 30 degrees. Plus DC. DC equals to R over times 37.5 degrees. So here DC equals to R over tangent 37.5 degrees. In conclusion, we found out that 2 equals to R over tangent 30 degrees plus R over tangent 37.5 degrees. So 2 equals to, here we take out R as a second factor from those two expressions. So what is left from R over tangent 30 degrees after we took from it R as a second factor? What is left is actually 1 over tangent 30 degrees. And what is left from R over tangent 37.5 degrees after we took from it R as a second factor? What is left is actually 1 over tangent 37.5 degrees. In conclusion, we found out that 2 equals to R times 1 over tangent 30 degrees plus 1 over tangent 37.5 degrees. So 2 equals to R. Inside the brackets we have 1 over tangent 30 degrees. 1 over tangent 30 degrees equals to 1.732 plus 1 over tangent 37.5 degrees. 1 over tangent 37.5 degrees equals to 1.3032. So if we're going to find out the 2 equals to R times 1.732 plus 1.3032. 1.732 plus 1.3032 equals to 3.0352. So in conclusion, found out the 2 equals to R times 30352. Here we divide this equation by 30352, and finally we get that R, the radius that we are looking for, the radius of the circle that is described by triangle ABC, equals to 2 over 30352, and 2 over 30352 equals to 0.6589. In conclusion, we found out that R equals to 0.6589 units. Repeat again. In both methods, we found out that the radius R of this circle equals to 0.6589 units. In the next step, I'm summarizing the lecture. We start with the first method, of course. In this lecture, we found out the radius R of this circle that is inscribed by triangle ABC. So in the drawing we have triangle ABC that blocks this circle, and we know that this angle ABC equals to 60 degrees, and this is angle ACB that is equals to 75 degrees. In addition, we know that side BC equals to 2 units in its length. Again, our mission is to find out the radius R of this circle. So, in the first method, we did a construction, that is to say, from point C, we draw perpendicular on side AB. This is the perpendicular. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. When doing this construction, we created the right triangle DBC, so I copied the right triangle DBC in a new page and we analyze this right triangle, triangle DBC. Actually, this is the right triangle DBC that I copied from the original drawing. This angle equals to 60 degrees, and the side BC equals to 2 units according to what is given as the question. So in this right triangle DBC, cosine 60 degrees equals to dB over BC. Cosine 60 degrees equals to dB over BC. So it is dB over BC. BC is 2, so we substitute BC by 2. So in conclusion, found out that cosine 60 degrees, that is 1/2, equals to BD over 2. 1/2 equals to BD over 2. We multiplied this equation by 2 and finally found out that BD equals to 1 unit in its length. Here, this line segment BD equals to 1 unit in its length. We continued to focus on the right triangle DBC, this right triangle DBC. On this right triangle DBC, sinus 60 degrees equals to DC over BC. Again, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is equal to 3 over 2, and it is equals to DC over BC. BC is 2. So in conclusion, found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2 and finally found out that DC equals to the square root of 3 units inside. Here. So you can write down in the original drawing that side, this side 7 DC equals to the square root of 3 units inside. We continue to focus on the right triangle DBC. On the right triangle DBC, the sum of the angles must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside the right triangle DBC? We have this angle that is the right angle, this is equal to 90 degrees, plus this angle that is 60 degrees, 90 degrees plus 60 degrees is equal to 150 degrees, therefore the missing angle here must be equal to 30 degrees. In order to complete the sum of the angles in this right triangle 280 degrees, the missing angle here must be equal to 30 degrees. So the small angle DCB equals to 30 degrees. The big angle in the red line, this is angle ACB, equals to 75 degrees. The big angle minus the small angle must be equal to this missing angle. So the missing angle, that is angle ACD, equals to the big angle that is 75 degrees minus the small angle that is 30 degrees. 75 degrees minus 30 degrees is equal to 45 degrees. So the missing angle ACD equals to 45 degrees in its size. Then I copied the right triangle ACD in the new page and we analyze this right triangle, triangle ACD. This is the right triangle ACD that I copied from the original drawing. We just right now found that this angle equals to 45 degrees in its side, and we already found out that side DC equals to the square root of units in its length. The sum of the angles in this right triangle, triangle ADC, must be equal to 180 degrees. So which angles we have inside the right triangle ADC? We have this angle that is equal to 90 degrees, plus this angle that is 45 degrees. 90 degrees plus 45 degrees, it is 135 degrees. Therefore, the missing angle here must be equal to 45 degrees. In order to complete the sum of the angles in this right triangle ADC to 180 degrees, the missing angle here must be equal to 45 degrees. So those two angles are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So those two sides that are located in front of those two equal angles must be also equal to each other. That is to say, side AD must be equal to side DC. AD equals to side DC. Well, already found out that DC equals to the square root of units, so we can write here that DC equals to the square root of units, and from this equation AD equals to DC equals to the square root of units. We will derive that side AD also equals to the square root of units in its length. Here side AD equals to the square root of units in its length. You can write down in the original drawing that this is side AD, that is equals to square root of units in its length. We continue to focus on this right triangle, triangle ADC. We implemented here the Pythagoras theorem in order to find out the hypotenuse AC. According to the Pythagoras theorem, AC squared equals to AD squared plus DC squared. So AC squared, that is the square of the hypotenuse, equals to AD squared. AD squared to 3, therefore AD squared squared to 3 squared, that is 3. Plus DC squared. DC is also square root of 3, therefore DC squared squared to 3 squared, that is 3. So in total AC squared equals to 3 plus 3, that is 6. So AC squared equals to 6. We took a root out of this equation. And finally found out that AC, the hypotenuse AC equals to the square root of 6 units in its length. So we can write down here in the original drawing that side AC of triangle ABC equals to the square root of 6 units in its length. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by triangle ABC is equals to the radius R equals to the area of triangle ABC over S, that is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of any triangle is the perimeter over 2. And the perimeter of any triangle is the sum of its side lengths. The drawing of this rule number 15 is here. This is the drawing, and we have here a circle with radius R that is described by this triangle, triangle ABC, or triangle ABC blocks this circle. So the radius R, according to this rule number 15, will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. You can implement rule number 15 in our drawing. Why? Because whenever you have a circle that is inscribed by a triangle, you can implement rule number 15. Therefore, you can implement rule number 15. So the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Repeat again, the radius R of our circle, the radius, that is the radius that we are looking for in this question, is equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. So the the area of any triangle is the base of the triangle times the height to the base over 2. And we have to divide the area by S, that is the semi-perimeter of the sub-triangle ABC. We choose the base of this triangle ABC as AB, and therefore the height to the base must create 90 degrees with the base. So the height to the base is CD, because it's created 90 degrees with the base AB. Repeat again, the base is AB, the height is CD, and we have to divide it by 2 in order to get the area of triangle ABC. So in total, this expression equals to the area of triangle ABC, and we have to divide it by S, that is the semi-perimeter of the same triangle ABC. The semi-perimeter of any triangle is the perimeter over 2. That is to say, the semi-perimeter of this triangle ABC will be equal to AB plus AC plus BC over 2. Repeat again, the semi-perimeter of triangle ABC equals to AB plus AC plus BC over 2. So here we have AB is equal to 3 plus 1 times CD. CD is equal to 3, and we have to divide it by 2. And it is equal to AB. AB is equal to 3 plus 1 plus AC. Here AC is equal to 6. Here AC is equal to 6 plus BC. According to what is given in the question, BC equals to 2 units inside. So substitute BC by 2. And we have to divide it by 2. So this expression is the area of triangle ABC, and the value of this expression in total is equals to 2.366 square units. That is the area of triangle ABC. And this expression in total, it is the semi-perimeter of the triangle ABC. And the value of this expression it is equals to 3.591 units. And 2.366 over 3.591 equals to 0.6589. So in conclusion, found out that the radius R, that is the radius that we are looking for this circle, is equals to 0.6589 units. Okay, we finished with the first method. In the next step, I presented to you how to find out the radius R of this circle according to the second method. In the second method, we define the center of this circle, this point as O. We define the point of tendency of tangent AB with this circle as C. We define the point of tendency of tangent AC with this circle as F. And finally, we define the point of tendency of tangent BC with this circle as D. Then we join points O and D together by a set line. Point O is the center of the circle, point D is the point of the circle itself. Therefore, all D is the radius of this circle that is equal to R according to our definition. And we have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, then this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. Likewise, we join points O and D together by a straight line. OE is the radius of this circle that is equal to R. The radius OE is on to point E, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is on to the point of tendency, then tangent AB will be perpendicular to the radius EO. If AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to the same rule, rule number 1. And finally, we join points O and F together by a straight line. OF is the radius of this circle that is equal to R. The radius OF is drawn to point F, that is the point of tendency of tangent AC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius FO. If AC is perpendicular to FO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then I presented to you rule number 2 and implemented rule number 2 in our drawing. if we focus on the common standpoint point C, from the common standpoint point C, we have two tangents to the second, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD according to rule number 2, if CF equals to CD according to rule number 2. Likewise, we focus on the common standpoint point B. From the common standpoint point B, we have two tangents to the second, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. That is to say, B equals to BD according to the same rule, rule number 2. Then we join points O and C together by side line, and we join points O and B together by side line. In the next step, we proved that the yellow triangle is congruent to the green triangle. So why those two white triangles congruent to each other? First of all, EO equals to OD. They are both the radii of the circle, therefore they are equal to each other. In addition, BE equals to BD according to rule number 2. BE equals to BD according to rule number 2. And finally, BO is a common side that belongs to both triangles, so BO equals to itself is a common side that belongs to both triangles. So actually prove that all the three sides of the yellow right triangle in BO are correspondingly equal to all the three sides of the green right triangle BOD. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be equal to each other. So if this angle is theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta must be equal to 60 degrees. That is to say 2 theta equals to 60 degrees. Yeah, we have 2 theta equals to 60 degrees. We divided this equation by 2 and finally found out that theta equals to 30 degrees in its size. This is angle theta that equals to 30 degrees in its size. Then I copied the right green triangle ODB, this right green triangle ODB in the new page, and we analyze this right green triangle ODB. This is the right green triangle ODB that I copied from the original drawing. This is an angle theta that is equal to 30 degrees in its size, and side OD equals to R because it is the radius of the circle. In this right triangle ODB, times 30 degrees equals to OD over DB. That is to say, times 30 degrees equals to OD, that is R, over DB. Here we multiply this equation by BD and finally found out that BD times 30 degrees equals to R. Here we divided this equation by times 30 degrees and finally found out that BD equals to R over times 30 degrees. Here, this line segment BD equals to R over times 30 degrees in its length. Then we repeated on the same process on those two right triangles. Those two right triangles can go into each other according to side rule. I will repeat on the process quickly, on the same process actually. OF equals to OD, because they are both the radii of the circle, therefore they are equal to each other. In addition, CF equals to CD according to rule number 2. Here CF equals to CD according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. So I prove that all the three sides of the right orange triangle OFC are correspondingly equal to all the three sides of the right orange triangle ODC. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. That is to say, 2 alpha equals to 75 degrees. We divided this equation by 2 and finally found out that alpha equals to 37.5 degrees. So actually this is angle alpha that is equal to 37.5 degrees. Then I copied the orange right triangle ODC in a new page and we analyze this right orange triangle ODC. This is the right orange triangle ODC that I copied from the original drawing. This is angle alpha that is equal to 37.5 degrees in its size, and side OD is the radius of the circle that is equal to R. In this right triangle ODC, times 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. R over DC. Again, tan is 37.5 degrees equals to R over DC. Here we multiply this equation by DC and found out that DC times tan is 37.5 degrees equals to R. Here we divided this equation by tan is 37.5 degrees and finally found out that DC equals to R over tan is 37.5 degrees. Here this line segment DC equals to R over tan is 37.5 degrees. For the drawing, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. Here. BC equals to BD plus DC. BC equals to 2 according to what is given as the equation, so substitute BC by 2. BD is R over tan is 30 degrees. Here, BD equals to R over tan is 30 degrees plus DC. DC equals to R over tan is 37.5 degrees according to what we have already found out. Here, DC equals to R over tan is 30 degrees. So in conclusion, found out that 2 equals to R over tan is 30 degrees plus R over tan is 37.5 degrees. So 2 equals to, here we took out R, a second factor from those two expressions. So what is left from this expression after we took from it R as a second factor? What is left is actually 1 over tan is 30 degrees plus R over tan is 37.5 degrees. What is left from this expression after we took from it R as a common factor? What is left is actually 1 over tan is 37.5 degrees. So in conclusion, found out that 2 equals to R. Inside the brackets we have R over tan is 30 degrees plus R over tan is 37.5 degrees. So 2 equals to R, and again inside the brackets we have 1 over tan is 30 degrees is 1.732 plus 1 over tan is 37.5 degrees is 1.3032. So in conclusion, found out that 2 equals to R. Inside the brackets we have 1.732 plus 1.3032. 1.372 plus 1.3032 equals to 3.0352. So in conclusion, found out that 2 equals to R times 3.0352. We divided this equation by 3.0352 and found out that R, the radius that we are looking for, the radius of the circle, equals to 2 over 3.0352, and 2 over 3.0352 equals to 0.6589 units. So in both methods we found out that the radius R of this circle equals to 0.6589 units. Okay, thank you very much.